Hi everyone, this is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So in this session, we are going to discuss about some problems based upon how to find out the atomic radius, density of the given system or the given material. So first we'll see how to calculate the volume of an FCC unit cell in terms of atomic radius. Okay, now if we see this problem, so in this problem we have to calculate the volume of an FCC, face-centered cubic structure, in terms of atomic radius. So how to calculate the given structure? So in this example we have face cubic crystal structure. So for this FCC structure, we need to find out the volume in terms of atomic radius. Okay, so this is the figure we have given to us. So this is a FCC type of crystal structure. How can you identify the given structure as FCC? So in the previous sessions we have discussed about FCC, BCC and HCP. Now in this case, FCC can be defined as the object, the face is exactly to the center. That means all the corners, all the four corners are being bonded. So that's why it is called as a face centered. If any face, whether it is a front side, back side, upper or bottom, any face if you see, exactly it is the center, and from the center it is bonding to all the corners. So that's why it is called as an FCC crystal structure. So in this problem, what are the data we have? First of all, the length is given as small a. This is the chord length which you have. The chord length is given as A. Since it is a cube, all the sides are equal. Since it is a cube, all the sides are equal. That's why any side if you see, it is A. All the sides. All the sides, the value is A. The chord length is equal at all the sides. Since it is a cube, that's why we have A value. Now, the radius of the corner from the center is given as capital R. So each corner is having R. All the four sides. Okay. And what is the other data we have in this problem? The complete diagonal radius is 4R. How we are getting 4R? Now if you see it, so each corner is having the radius of capital R. Okay, so this is R, and here also you can get R, R and R. So R plus R plus R plus R. So total how many? 4R. So the diagonal length, the diagonal radius is 4R. So this is the data available for us. For this given data, we need to find out what is the volume of this FCC in terms of atomic radius. Now we'll see how to solve it. Now, first point is what? The atom touches one another across the phase diagonal. Is it not? Each atom is being contacted to the another across the phase diagonal. So what is the length across the phase diagonal? So this is the diagonal and this is the diagonal. So across the diagonal, what is the face length? So total, as I told, each corner is having R, R, R. So what is the total? You are getting 4R. So the atom is touching one another across the face diagonal. So diagonal is very, very important here. Diagonal. Okay, with this diagonal, the total length is 4R. Next, because the unit cell, so what are the unit cell given to us is a cubic structure, is it not? Since it is a cubic structure, so what will be the volume of the cubic structure? It is A cube. Since the diagonal, the lengths, the chord lengths are given in terms of A, the chord lengths are given in terms of A, so the volume of the cube will become A cube. So that's why the volume of the unit cell given to us, since it is a cube, therefore the volume will be A cube. So what is A here? A is nothing but the cell edge length. So this length, the edge length or the chord length is called the A for this cube. And what is the other data we have now? Now from the right angle triangle on the face. So what is the right angle triangle from the face? So this is the right angle triangle what we have. See this figure clearly. So this is the right angle triangle what we are getting from this FCC cubic structure. So now you apply the Pythagoras theorem for this. So what you are getting here, a square plus a square is equal to 4r square from this right angle triangle. That means 4r, this length is equal to under root of a square plus a square. Okay, now if you square on the both sides, what you're getting, this root and square will get cancelled, then you'll get 4r square is equal to a square plus a square. So this is what we are getting from this right angle triangle. So if you solve this further, if you solve this, then we are getting as a is equal to 2r into root 2. So how we are getting that 2r into root 2? A square plus a square is equal to nothing but 2a square. 2a square is equal to 4r square. Is it not? From this equation. And from this, what is r square by a square? It is 4 by 2. So you are getting 2. So r square by a square is equal to 2. And from here, r into 2 into root 2 is equal to a. So this is what you are getting. So the same thing you are writing here. A is equal to 2 into r into root 2 if you do the further solving of that equation. Now, as we know that what is the volume of the cube, we have a cube. So we are writing the volume of the cube is equal to Vc, and that Vc is nothing but a cube. This is the volume of the given crystal structure. That crystal structure is a cube. Now what is the a value? A value we are getting it as 2r into root 2. Okay, so this is the equation of a from the right angle triangle. We are getting as a equal to 2 into root 2 r. Now since we know that the volume of the cube is a cube, now substitute the value of a in this equation. If you substitute the value of a in this equation, then what you are getting here, Vc is equal to a cube. A is nothing but 2r into root 2. If you do the whole cube for this, you are getting 16r cube into root 2. So this is the volume of the given FCC structure. For that, we are trying to find out what is the volume. So this volume is in terms of radius. So what is r here? R is nothing but the radius. So we are trying to find out what is the value of the volume of the given crystal cube in terms of atomic radius, capital R. Yes. Now, very simple for us, a volume is given to us. That volume is in the form of a cube. So for this cube, we need to find out the volume in terms of atomic radius. So how to find out? Step by step, we'll understand again how to solve the volume of the cube in terms of atomic radius. Now try to see the figure, observe clearly how many corners each face is being bonded to another. So how many here? 1, 2, 3 and 4. Okay. And see diagonally along the diagonal face, what is the total length of that atomic radius? So what is the total length here? This is the diagonal face. That is the diagonal face. For this diagonal, what is the total face length? Since we have each radius as small r, so to each point it is having r, and this circle again you can divide. So this is r, this is r and this is r. So totally 4r you are getting. So the same thing is there along the diagonal. So first point we got, that is the face diagonal length. Diagonal, that is very, very important. The face diagonal length is 4r. Next, since the unit cell is in the form of a cube, so what is the volume of the cube? It is in terms of cubic you have to write. Now, what cubic you have to write here? Since the length, edge length is mentioned as a. So since it is a cube, all sides are equal. So volume will be a cube. All the three sides, a into a into a. So it is a cube. Okay, the volume of the cube is A cube. Now we have to try to find what is the value of A. How can we find out the value of A? So we have the reference in this figure. You can see a right angle triangle is being formed like this. A right angle triangle you can form with the help of this FCC. Now what is the edge length here? It is A, and here also A. What is the diagonal? It is 4R. Now if you apply the Pythagoras theorem for this, so you can write as A square plus A square is equal to 4R square. So this is what you are getting. Now from this, try to solve for the R value or A value. So if you solve for that, you are getting A is equal to 2R into root 2. That means you are getting the chord length or the edge length in terms of radius. Now this A, you can substitute the value of volume. So what is the volume of the cube? It is A cube. Okay, in terms of A, you substitute the value of A as A cube. So like this. So volume of the cube, we are trying to write it as VC, and VC is equal to A cube. Now what is the value of A here? 2 root 2 into R. The same thing you are substituting here. We are trying to get in terms of cubic to get the volume. So what you are getting ultimately? 16 R cube into root 2. So this is the value of the given cubic structure with FCC to find out the volume in terms of atomic radius. Therefore, VC is equal to 16 R cube into root 2. So this is the final value. Next, if you go to the other problem, so this problem is based upon the atomic packing factor. So the theory which is related to atomic packing factor, atomic radius, all those things we have discussed in the previous sessions. Now we are trying to solve how to find out those atomic packing factor value or atomic radius in this session. The second problem is based upon the atomic packing factor of the given FCC crystal structure. Okay, so what is the problem given to us here? Show that the atomic packing factor of FCC crystal structure as 0.74. So this we have to prove. For the FCC, for the given FCC, we have to prove that the atomic packing factor value as 0.74. So as we all know that for the solid sphere, okay, the atomic packing factor is defined as the volume of atoms in a unit cell to the total volume in the unit cell. So this is the atomic packing factor value. So what is the atomic packing factor? Is defined as the ratio of volume of atomic atoms in a unit cell. So how many atoms are there in a unit cell to the total unit cell volume. So that is the atomic packing factor. So APF is nothing but atomic packing factor. So that is given by Vs by Vc. Vs by Vc. Vs is nothing but the volume of atoms in a unit cell. So unit cell also we have discussed in the previous class. So volume of atoms in the unit cell to the total unit cells in volume. So now both the atoms and the unit cell are being calculated in terms of atomic radius. So therefore the volume of the sphere is what? 4 by 3 pi r cube. So since we are calculating all the volume in the unit cell as well as the total unit cell in a volume, which are being in terms of radius, atomic radius we are trying to find out. So we are trying to write the volume of the sphere in terms of radius also. So that's why the volume of the sphere we are writing in terms of radius as 4 by 3 pi r cube. Now, because these three, since it is the FCC, so in FCC what is happening? All the four corners are being in bonding. Okay, that's why the 4 atoms, for 4 atoms per the FCC unit cell. So how many you are getting? 4 corners. So the volume is multiplied with 4 times. Volume of the sphere is multiplied with the 4. Why? Because at all the 4 corners the unit cell is being bonded. So how we are writing this equation? Vs as 4 into the volume, 4 by 3 pi r cube. So how much you are getting? 16 by 3 pi r cube is the volume of the sphere of a given FCC. Okay, in general the volume of the sphere is 4 by 3 pi r cube. But since here what is happening, since it is an FCC, so again depending upon the type of crystal structure, whether it is FCC or BCC or HCP, you have to find out how many sides the unit cell is being contacted or it is being bonding. To that you have to multiply this volume. So since it is in cubic, at all the four corners, the face is being exactly at the center. So for all the four corners, it is being bonded. So that's why you are multiplying the volume of the sphere into 4 times. So 4 into 4 by 3 pi r cube. So how much you are getting? 16 by 3 pi r cube. So this is the total volume. Now in the previous problem, we have calculated the total volume of the given unit cell as we have got just recently. It is 416 r cube into 2. So this is the value of the volume of the FCC. Now what is the definition of the atomic packing factor? It is Vs by Vc. Okay, Vs by Vc is the atomic packing factor. So what is the Vs? Just now we got as we are multiplying that volume into 4 times. So 16 by 3 pi r cube, that is the Vc value. And what is Vs? 16 r cube and root 2. So if you multiply, if you do the division, you are getting it as 0.74. So this is how you have to calculate the atomic packing factor of the given FCC. So we have proved this as 0.74. Okay. So again, if you go through this question again, so they're asking to prove that the atomic packing factor of the given FCC as 0.74. So before starting the problem, we have to know what is the atomic packing factor. What is the definition for the atomic packing factor? So atomic packing factor is nothing but the ratio of volume of atoms which are being present in the unit cell to the total unit cell volume. So this is the formula or the definition for the atomic packing factor. So that is Vs by Vc. Vs is nothing but the how many atoms are there in a unit cell in terms of volume. And what is Vc? It is the total volume of the unit cell. Okay, so this is the definition for the atomic packing factor. Now, since we have to calculate the Vc and Vs in terms of radius, so we have to try to write the volume of the sphere in terms of radius. So, what is the volume of the sphere in terms of radius? It is 4 by 3 pi r cube. This is predefined. Okay, now this volume of the sphere, at how many corners it is being bonded? We have to calculate it. So, how many corners for the FCC? If you see the FCC of a cubic crystal structure, okay, the body is being contacted or bonded to all the 4 corners. Exactly the 4 corners it is being bonded. So that's why these 4 corners have to be multiplied with the volume of the sphere. That's why you're writing it as 4 into 4 by 3 pi r cube. So therefore you're getting it as 16 by 3 pi r cube. So from here we have got what is the volume of the sphere, that is Vs. Now what is the other value we have to find, that is Vc. What is the Vc? Vc is nothing but the total volume of the unit cell. The total volume of the unit cell we have calculated just in the previous problem in terms of atomic radius as Vc is equal to 16 r cube into root 2. Now we have got these two values to find out the atomic packing factor. So atomic packing factor is Vs by Vc. So what is Vs here? 16 by 3 pi r cube to Vc. What is Vc? 16 r cube into root 2. So if you do the solution for this, you are getting it as 0.74. So hence we have proved that the atomic packing factor of the given FCC cubic structure as 0.74. Next comes the density. How to find out the density? How to compute the density? So density is nothing but how much dense the given crystal structure is there, whether it is a fully dense or partially dense. So you can find out the density by this formula. So if you know the knowledge of the density, then you can easily define the properties of the material. So a knowledge of the crystal structure of a metallic solid permits the computation of its theoretical density by the relation as rho is equal to small n into capital A by Vc into Na. So density refers to the rho value. So this is the density. Small n refers to number of atoms. Capital A refers to the atomic weight. Vc refers to, just now we have discussed about Vc, volume of unit cell. Na is nothing but Avogadro's number. This is a constant value. So this is how you have to calculate the density of the given crystal structure. That is, rho is equal to Na by Vc into Na. So small n refers to the number of atoms. Capital A refers to the atomic weight. What is the denominator value? Vc into Na. What is the Vc? Vc is nothing but the volume of the unit cell, and A is the Avogadro's number, that is 6.22 into 10 power 23 atoms per 1. Okay, this is how you'll find out the density of any given crystal structure. So this is very important. If you know the density, then it is very easy for us to calculate the properties of the given materials. Now coming to the other problem, which is based upon the density. So what is the question given to us here? Copper has an atomic radius 0.128 Newton meter, an FCC crystal structure, and an atomic weight of 63.5 grams per mole, and compute its theoretical density and compare the answer with its measured density. Okay, now here copper is taken as an example to find out what is the density value. For this density value, what we have to do? We have to find out the density and we have to compare with the measured value. Okay, already some measured density values are being predefined, and that measured density value you have to compare with the given data for us now. So what is the data given for us now? In this case, the atomic radius of the copper as 0.128 Newton meter, and it is an FCC, again phase cubic structure, and the atomic weight of the copper is given as 63.5 grams per mole. And for this given data, you need to compute the theoretical density. Okay, with the problem, with this given data, whatever the formula we have, you have to incorporate the values and find out the theoretical density value. And this theoretical density value you have to compare with the already measured density value of the copper. Okay, this is the question. So first try to understand what is the thing which is being asked in the question, and then try to find out the given data, and from that given data use that formula and you have to substitute, and what are the other terms required, try to bring out from the given data. Now if you see the solution for this, since it is a cubic structure, that's why read the question clearly, whether it is FCC, BCC or HCP. Now in this case, since it is an FCC, so since it is a crystal structure with an FCC, how many number of atoms you have per unit cell? You have 4. Okay, so since the crystal structure is FCC and the number of atoms per unit cell is 4, and what is the other data we have? Furthermore, the atomic weight of the copper is given as 63.5 grams per mole. So that is the other data we have, and the unit cell for the FCC we have known as, it is Vc is equal to 16 r cube into root 2. And what is the other data we have? We have the data as a radius, atomic radius is also given as 0.128 Newton meter. So we have the radius as 0.128 Newton meter, and Vc we know it as 16 r cube root 2, and number of atoms, since it is a cubic structure FCC, we have 4, and the atomic weight is also given as atomic weight 63.5 grams. So these are the data which is available for us. Now taking these values, you have to substitute in the density formula. So what is the density formula we have? Density is nothing but rho is equal to small n into ACU, that is atomic weight, to the volume of the unit cell into the Avogadro's number. Okay. So what is n value here? How many atoms we have per unit cell? Since it's a cubic structure, you have 4. So that's why 4 atoms per unit cell. And next is the copper atomic weight, which is given as 63.5 grams per mole. So this is also we got. And to the denominator, what is Vc? Vc is nothing but the volume of the unit cell. So what is the volume of unit cell? 16 r cube into root 2. Okay, this is the volume. But what is r again here? We have r as 1.28 into 10 power minus 8. Okay, we are substituting r value. We are replacing that r into 1.28 into 10 power minus 8 whole cube per unit cell. And what is the Avogadro's number? So this is a constant value, 6.022 into 10 power 23 atoms per mole. So if you substitute all the values, all the given values in the density formula, so we are getting it as 8.89 grams per centimeter cube. Okay, so this is the theoretical value of the copper density value. And this density value, now what we have to do, we have to compare with the already calculated value, already measured value. So this is the theoretical value what you are getting. Okay, now since we have a predefined value of the copper, which is 8.94 grams per centimeter cube. Okay, now this is very close to this 8.89, which is almost close to 8.894. That's why this agreement of result is very close to each other, and thus both the values are same. Okay, this is how you need to find out the density of any given material. So we'll see again the problem, how to solve. So first of all, try to understand the question. So in this question, they're asking FCC. Okay, FCC crystal structure of a copper material which is having some atomic radius as 1.2128 Newton meter, and atomic weight is also given as 63.5 grams per mole. So for this given data, you need to find out the density of the copper theoretical value, and this theoretical value you have to compare with the already measured value and see whether there is a huge gap. If there is a lot of gap between these two, then the results are not correct. If they are very nearly close to each other, the theoretical value as well as the measured value, then whatever the things we are calculating, it is almost close and it is a valuable question. And now for this, since it is an FCC, how many corners, how many number of atoms we have per unit cell is nothing but 4 for all the 4 corners. So total atoms in a unit cell we are having as 4. Next, atomic weight of the copper is given as 63.5 grams per mole. And next, what is the volume of the sphere, volume of the cube? We have 16 r cube into root 2. And what is the other data we have? Atomic radius. So try to list out each individual data, whatever the data is given in the problem. And after that, write the equation of the density. So this is the equation of the density, rho is equal to N A by Vc into Avogadro's number. So what is small in here? Atomic weight. Okay. Small a is nothing but capital A is atomic weight. Small n is nothing but how many atoms per unit cell. So how many atoms you have per unit cell? Here you have 4. That's why 4. What is the atomic weight? 63.5 grams per mole. Next, what is the denominator value here? Vc. Vc is nothing but 16 r cube. So what is value of r here? 1.28. R is nothing but 1.28 10 power minus 8 centimeters. So r cube. So cube into the Avogadro's number, that is 6.022 into 10 power 23. So if you calculate, we are getting it as 8.89 grams per centimeter cube. So this is the theoretical value what we are getting. Now this theoretical value we have to compare with the measured value of the copper. So what is the measured value of the copper? It is 8.94 grams per centimeter. So it's almost close to your measured value. Since the theoretical value is almost close to the measured value, hence our results are approximately correct. So this is how we can close the agreement since the results are being similar to each other. So next topic is about polymorphous and allotropy. So what is polymorphous? So some metals as well as non-metals have more than one crystal structure. Okay, if the metals which are having more than one crystal structure, then those types of materials are called as a polymorphous material. Okay, if any metal or non-metals are having more than one crystal structure, these are said to be polymorphous material. And coming to the allotropy, what is allotropy means? When these polymorphous type of elements are found in solids, what are the polymorphous elements are there? If these elements are found in solids, then that materials are said to be allotropy. Okay, so first is what? Polymorphous. Polymorphous is nothing but when a metal or non-metals which are having more than one crystal structure, these are said to be polymorphous. And these polymorphous material which are observed in a solid material, then those type of materials are called as a allotropic materials. And these allotropic materials are mainly depend upon the how much temperature you are giving, how much amount of pressure you are giving on the material. That depends upon this allotropy. If you take the simple example to define or to differentiate between the allotropy, so you take the example of carbon. So in carbon we have graphite. Okay, so it is a stable polymorphous material under ambient conditions. Under normal temperature conditions, it is a stable polymorphous. It won't change its crystal structure. But in case of diamond, okay, in case of diamond, what is happening? It changes. It changes with the pressure or with the temperature. So like that, you have different types of polymorphous or allotropic material, which is highly dependent upon the temperature as well as the pressure. Also, if you take the examples of a pure iron, which is having a BCC crystal structure, so at room temperature, again at ideal temperature or ambient temperature, it will change to FCC. From BCC, it will convert to FCC at 167 degree Fahrenheit or 912 degrees centigrade. Okay, at normal ambient temperature, it won't change. But if you heat that iron, pure iron to 900 degrees centigrade, what is happening? The BCC is being slowly shifted to FCC. So that is how the materials which are having more than one crystal structure are said to be polymorphous. And how we are achieving those polymorphous? These polymorphous materials are being highly dependent upon the temperature as well as the pressure values. So if you apply high amount of pressure, the iron, what are the iron we are taking an example, initially it was in BCC, now after above 900 degrees centigrade, slowly it is converting into FCC. So that is one of the criteria. So like that, this iron is having two different structures. From BCC, it is being converting to FCC. So this is one of the example of polymorphous. And in which factor it is depending? It is depending upon the temperature. Similarly, if you consider about the graphite or the diamond, on the pressure, it is being depending. In the ambient conditions, the diamond is not being converted. It is in a stable condition, polymorphous condition. And but once if you change the pressure or temperature value, slowly it is being converting into polymorphous. It is changing its crystal structure. So those are the examples of the polymorphous and allotropy. And coming to the crystal systems, how to define the crystal structure? Systems means, see, if you heat any element, if you apply any pressure, so in what directions it is being deformed, whether it is in X direction, Y direction or Z direction. How can you tell? You can't tell that, yes, it is shifting towards this, like this, like this. No, you have to tell in a specific direction. In X direction, the material is being deformed. In Y direction, the material is being deformed. In Z direction, the material is being deformed. So in such a way that you have to explain the crystal systems, whether it is X direction, Y direction or Z direction, along these directions, at what angle it is being deformed. So that is also you have to explain. So that's why, because there are many different possibilities of the crystal structure, it is varying depending upon the temperature and pressure. We have to divide them into groups. According to the unit cell or the atomic arrangements. So since it is being varied in all the directions, try to make into groups according to the atoms per unit cell. So that type of scheme, it is based upon the unit cell geometry. So again, geometry, how can you define this geometry? Depending upon the x, y, z coordinate system. So since we are dividing that into an unit cell, depending upon the atoms present in the unit cell, and these atoms which we are dividing per unit cell have to be in a particular shape, okay, whether it is in x direction, y direction, or z direction. So that is why we are taking a framework with an example which is having a coordinate system of x, y, z. So this is what are the dotted line you are seeing. This is y direction, z direction, and x direction. Okay, and this is the origin of the unit cell, and x direction, this is x, this is y, and this is z. Now A, B, C are the sides, lengths, edge lengths of the given cube, and alpha, beta, gamma are the angles from the center. Now once you apply the pressure or temperature on the given body, now I can easily tell that yes, this body is being deformed in x direction at some 30-degree angle. Suppose in another direction, this object is being deformed along y direction with 45 degrees. Another thing, we can tell that along z direction with some 70 degrees centigrade. So like that, if you want to define the deformation of any given body, you have to take some reference. So here the reference is x, y, z coordinates, and alpha, beta, gamma are the angles, at what angles it is being deformed. By taking the reference, and also at what angles, at what inclination the body is being deformed, it is easy for us to define these with the help of crystal systems. So this is a unit cell with x, y, z as the coordinate axis, and also the axial lengths as A, B, and C. A, B, C are called the axial lengths, and here you have the alpha, beta, gamma. These are the interaxial angles. Interaxial angles. Now the unit cell geometry is completely defined in terms of 6 parameters. Is it not? What are the geometry of the unit cell we have? Totally we have A, B, C, that is 3, and alpha, beta, gamma, again 3. So 3 plus 3 is 6. So in terms of 6 parameters, in terms of these A, B, C, alpha, beta, gamma, we are trying to define the geometry of the given unit cell. So what are those? Those are the edge lengths A, B, and C. A, B, C are called the edge lengths, and the 3 interaxial angles, what you are having, alpha, beta, and gamma. So total 6 geometries. Okay, 6 parameters we have to define the geometry of the given unit cell, and these are which are integrated and which are indicated in the given figure, and this is in terms is represented as lattice parameters. Okay, these are also called as a lattice parameters. So alpha, beta, gamma, A, B, C are also called as a lattice parameters. So on the basis of these, we can try to give some combinations. 7 different combinations can be achieved. So if you vary A, suppose first condition is A, B, C are equal, so you will get 1 parameter. So in some cases A equal to B and B is not C, you are getting other parameter. So like that, in the same way, the angles also if you shift, that is one other parameter. So if you change like this, totally we can get 7 different parameters based upon the interaxial angles as well as the edge lengths A, B, C and alpha, beta, gamma. So based upon these 7 parameters, we are trying to get some different forms, 7 different possible combinations with these. So what are those things? We'll see. So first one is the cubic, second one is the tetragonal, third one is the hexagonal, fourth is orthorhombic, fifth is rhomboid, sixth is monoclinic, and the last one is triclinic. So these are the 7 possible combinations we are getting from those 6 parameters. So one by one we will see how we are getting. So these are the lattice parameters, relationships, and the figures which are showing in unit cell geometry for the 7 crystal structure. So first one is the cubic crystal structure. So in general, cubic means all the sides are equal. So that's why first one is crystal structure, that is a cubic. In this axial relationships are A, B, C are both three are equal. All the edge lengths are equal to each other. That's why it is a cube. So and also the interaxial angles are equal to 90. Alpha is equal to beta equal to gamma is equal to 90. So that's why if you observe all the edge lengths are represented by A. Why A means since all the equal lengths A equal to B equal to C, that's why it is A. And everywhere if you see you are getting 90. Okay, the interaxial angles are 90 degrees. So this is called as a cubic. So this is the first possible crystal system. And coming to the second, it is a hexagonal. Second one is hexagonal. In this case, you are getting A is equal to B and B is not equal to C. So second parameter. So here again alpha is equal to beta equal to 90 and gamma you are getting it as 120. Now if you see the figure A, that means A is equal to B here. C is having different length, that's why it is not equal. So this is C. And if you see the angle, alpha and beta are same angles and gamma is having different angle. So this is how you are going to define. That's why all these crystal systems are dependent upon on the 6 parameters, that is ABC and alpha, beta, gamma. So depending upon those 6 parameters, we are trying to get these 7 lattice parameters. So the third one is tetragonal. In this case also A equal to B and B is not equal to C. And alpha, beta, gamma again 90. Now if you see this figure, the geometry of the unit cell. So if you can see A and B are same, that's why A equal to A. And C is having different length, that's why it is C. And again all the angles are 90. Okay, so this is the tetragonal. Fourth crystal system is the rhombohedral or trigonal. So in this case, what is the axial relationship? A equal to B equal to C. And if you see the interaxial angles, AB is equal to alpha, beta, gamma are not equal to 90. All the three angles are not equal to 90 and A equal to B and B is not equal to C. Then that type of geometry is called as a rhombohedral or trigonal. So this is the representation of the unit cell geometry for the rhombohedral. So though A, B, C are equal, that's why A you are getting, but alpha, beta, gamma are not 90. So that is the condition of this. And coming to fifth one, orthorhombic. Orthorhombic, here A, B, C are not equal to each other. All three are not equal to each other, as well as alpha, beta, gamma is equal to 90. So these interaxial angles are same, but the chord lengths are not equal. So you can see here, since both A, B, C are not equal, that's why they are represented separately A, B and C. And of course, these angles are 90 degrees to each other. That is the orthorhombic. Coming to the sixth one, monoclinic. In this monoclinic, A, B, C are not equal to each other. So this is the condition you have to know. And what is the interaxial angles? Alpha and gamma are 90 but not equal to beta. Alpha and gamma are 90 but beta is different angle. Some other not 90, some other angle. So this is how you can represent the monoclinic. And coming to the last one, triclinic. Here A, B, C are not equal to each other. And if you see the interaxial angles here, alpha, beta and gamma are not equal to 90. Some other angles not equal to 90. So this is how you can represent the unit cell geometry. So these are all the 7 parameters, okay, with which you can get the crystal systems and you can draw the unit cell. So how we are getting all these things means based upon the 6 parameters. Those are the A, B, C, the chord lengths, and the interaxial angles alpha, beta, gamma. If you vary these interaxial angles along with the chord lengths, then you are trying to get these 7 different parameters. Those are nothing but your cubic crystal structure, hexagonal crystal structure, tetrahexagonal crystal structure, rhombohedral, orthorhombic, monoclinic and tricline. So these are the 7 different possibilities which we are trying to get based upon the 6 parameters. So these 6 parameters we can use to form different types of crystal structures, and with those help of the crystal structures we can form the interaxial relationships as well as the axial relationships. So based upon these axial and interangle relationships, you can try to incorporate the unit cell geometry and how you can represent by graphically. So this is how there is a use of crystal systems. And if you want to have the references of the crystal systems and the problems related to atomic packing factor, atomic radius, so these are the books you can refer. First one is the Introduction to Physical Metallurgy by Sidney Havner, and the second one is Essential of Material Science, Engineering and Technology by Donald, and the third one is Material Science and Metallurgy by Everest Publications, and the other book we have Material Science Engineering by William Castler. So these are all the references books you can refer, and you can get the information related to all the different types of formulas with related to FCC, BCC and HCP, and also how to find out the atomic packing factor, how to find out the atomic radius, how to find out the chord length of all the different structures, whether it is a face centered, body centered or hexagonal center. Okay, and also depending upon the interaxial angles, depending upon the chord lengths also, how can you define the unit cell? How can you give it the information, what is the relation between the alpha, beta, gamma and ABC, that is the interaxial angles and interaxial lengths. So between these lengths, you can try to get the new unit cell geometry. Okay, so these are all the things you can find out from this information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.